Welcome back. Now let's look at the fourth example problem in this topic, and this is also the last example problem. So here we meet again Professor Goldluck, who comes back to try to buy a house. So this is a problem statement. So Professor Goldluck wants to buy a house with at least 4 bedrooms and costing no more than $400,000. So we call houses that satisfy these two conditions admissible houses. And in this problem, we had a new twist. Professor Goldluck can choose to first commit to a house, and then later he can back out from the deal. So this is a little bit similar to you pay some deposit and then later you may decide you really see a much better house, so you are willing to forfeit the deposit and switch to the new house. So this is allowed in this problem. And Professor Goldluck's strategy is he divides the total number of days into two equal length phases. So again, we're in this setting where there are n days. Every day there's one house become available, and that house will be available for 2 days. So the house will be available on the day it comes to the market, and then it will remain available for the second day, and then it will no longer be available. So in the two phases, the phase one, Professor Goldluck will not allow any admissible house slip through if its PPSF is no more than half of the highest PPSF among all the houses he has seen. So it doesn't have to be admissible houses. So the highest PPSF, and if the current house is admissible and its PPSF is no more than half, then Professor Goldluck will not let that house slip through, meaning that either Professor Goldluck will commit to it, or he can wait until tomorrow because the house will still be available tomorrow, and then decide to commit it tomorrow. So in fact, it means that Professor Goldluck will make sure that this house is available, or he finds an even better house, then it's okay that this house is gone. So he will choose to commit to the house on the next day if by next day this is still the best admissible house. And in phase two, Professor Goldluck will not let any admissible house currently on the market slip through if either the condition for phase one is satisfied, or this house has the lowest PPSF among all seen admissible houses. So you can see Professor Goldluck in phase two gets a little bit more desperate. So even though this is not that good a deal in the sense that its PPSF is not is more than half of the highest PPSF he has seen so far, but so long as this has the lowest PPSF among all the houses that are seen, it is okay. So in a sense, there's also strategy-wise, there's also two phases. The first phase is before committing to the house. At this point, Professor Goldluck will, if he sees the house he should good enough for him to commit to, he can always wait until the next day and then commit to the house then, if that's still the best house. But after committing to the house, if he sees an admissible house that is a better deal than the one he has already committed, then he will buy it immediately. And here, by being a better deal than he already committed, we require the PPSF is 5.7 less than the PPSF of the committed house. So I acknowledge that the rules are a little bit artificial. So they are created in a sense to make the correct simulation challenging, non-trivial. So I almost feel kind of like apologizing for using the problem like this for introductory programming course. But at least this problem is an example problem. So I'm going to show you the code for dealing with this, and the hope is that you learn from the code how to sort of write complex logic in a sort of a more modularized way that's easier to understand and easier to modify. And the last problem in this topic, Professor Goldlach number 6, will be similar to this. So based on the code for this problem, you can modify it to get the correct code for that. So the modification is non-trivial, but at least I think it's easier than coming up with the logic for handling everything by yourself. So let's look at some sample input and output, because the logic is quite non-trivial. And so I encourage you to go through all the 5 samples provided in the with the problem to understand exactly what's going on. So here we are only going over 2 of them together. So these are we have 6 days, 6 houses, and day 1 the house is not admissible because it's too expensive. So we want house price less than 400,000. Day 2 the house is not admissible because it only has 3 bedrooms. We want at least 4 bedrooms. Day 3 the house is admissible and it has a PPSF of 200. But at this point, the highest PPSF is 300, and 200 is more than half of that. So therefore, this is not good enough yet on day 3. But on day 4, we switch into phase 2. So that's the second half of the 6 days, and we find the house available on day 4 admissible and have a PPSF of 180.75. So at this point, there are 2 admissible houses, and the house on day 4 has the lowest PPSF. That means house on day 4 is good enough for Professor Goldlach. So we want to make sure this house we don't let it slip through. So, but we don't have to commit to it yet because this house will still available on day 5. So on day 5, the house is not admissible because it only have 2 bedrooms. So at this point, we will commit to house on day 4 because it's good enough. And if we don't commit it the next on day 6, this will be gone, and we may not have a better house. So we commit to the house on day 5. We commit to the house that first became available on day 4, which is the one with a price 361,500. On day 6, the house is also admissible, and it has a PPS of 175, which is 5.75 less than the committed house over day 4. So that's good enough. It's significantly better than the committed house. So this satisfies the condition for us to switch. So we will buy the house that became available on day 6. And so we print out first that house information, and then we also printed out information for the house that we have committed to. So let's look at another example. Again, we have 6 houses. On day 1, the house is not admissible because it only has 2 bedrooms and it has a PPSF of 40. On day 2, the house is not admissible because it only has 3 bedrooms. We need 4 or more. PPSF of 50. On day 3, the house is admissible. It has a PPSF of 200. But at this point, this is the highest PPSF, so we're not really interested in this yet. On day 4, the house on day 4 is not admissible, and it has a PPS of 300. However, day 4 is already in phase 2. So in phase 2, we are willing to consider any house that has the lowest PPSF among all the admissible houses. In fact, at this point, we have only seen 1 house that is admissible. So so definitely it has the lowest price among all admissible houses because it's only 1. So we should commit to house on day 3 because we according to the strategy, we don't want to let this house slip through. So on day 4, we committed to the house on day 3, which has a price of 400,000. And on day 5, the house is admissible. It has a PPSF of 180.75. So this is significantly less than the committed house, which has a PPS of 200. So according to the strategy, we will immediately buy this house. We will not wait. We'll just buy it. So we buy the house that first became available on day 5 with the price 361,500, and we also print out the committed house, which is the house available on day 3. So in fact, the house on day 6 is also admissible and even better. However, because of the algorithm, we will not buy this house. And this aspect will be changed in the last Goldilocks problem. So you have to sort of make the change to the code to accommodate that. So I encourage you to try to solve this problem yourself. Spend at least half an hour to an hour on it before sort of continuing watching the video. So I want you to appreciate sort of the trickiness, the difficulty of getting everything right. So how do we handle this? The problem is quite complex. It's important to, in general, I find it helpful to first think about what are the state information we will need. So basically, what are the variable? What are the what kind of data we need to store so that we can do this simulation, the simulating with how the algorithm works correctly. So obviously we need to know which phase we are in. So this depends on the day number, so in which day we are in. And we need to store information of the committed house. If we have committed to a house, we need to store information for that. So in order to decide which house to buy, so should we store the information? Do we need to store information for the house that we decide to buy? So we decide to buy a house only when we already committed to a house and we saw one that's better, and then we will immediately buy that house. So instead of waiting until toward the end. So one way to simplify the logic is we actually don't need to store it. We simply print the information for the house and then return. So then this will simplify the code a little bit. And we obviously need to store the information of the house first available on the current day and also first available on the previous day. So at any point, we may keep track of information of 3 houses: the house of the current day, the house of previous day, and the committed house. And to use the algorithm, we need to store the highest PPSF among all the houses and the lowest PPSF among all the admissible houses that we have seen. So these are the information we need to store. So we will have variables for them, and then we need to update them correctly. So how do the state will affect what action to take? So there are 2 separate decisions. The first is to decide whether to buy a house. These will happen only when there's already a committed house. And then today's house is also admissible and is significantly better. So this is based on today's house. And we also need to decide whether to commit to a house. And these will depend on which phase we are in and then the associated conditions. However, because the requirement is that we don't let a good house slip through, so we never need to commit to the house today, except when we are in the last day, which we sort of commit and buy. We only commit to the house that are become available previous day. And then today we realize it's satisfied the condition and we're not seeing something better today. So then we need to commit to the house in order to ensure it's still available later. So commit to house will be only for the house for the previous day. So here, this is a part of the code for the solution. In fact, actually, the slide is slightly different from the code that currently in HackerRank. But the main goal of having this code is to introduce the Boolean, the concept of a Boolean type. So yeah, we keep track. So this shows that we need to keep track the maximum PPSF so far and the minimum admissible PPSF so far. So we explicitly use a face variable that will be either 1 or 2 depending on the day. So I keep track of days. So in fact, yeah, I guess I could use start with I equals 1, I less than equal to n. So then I will be exactly the day number. So as it is, the I is the day number minus 1, and this logic will compute the phase correctly. You can also use the if condition if you don't like using this arithmetic. So if I in certain range, phase will be 1, otherwise phase will be 2. Here, the admissible specify whether the current house is admissible. So this is will take a value either true or false. This kind of variables are known as Boolean variables. And in C and C++, the type is called a bool. So this is short for Boolean. And we use essentially the same kind of expression that we use, a conditional expression that we use in if statement, because they are evaluated to true or false. We can assign them and then sort of store this variable. So a house is admissible if the number of rooms is the number of bedrooms is greater than or equal to 4 and the price is less than or equal to 400,000. So by using this variable, then later we can simply refer to this, for example, this admissible, instead of keep repeating this condition, in which case we may type it wrong. And also, this will make the code easier to read, because if you see near the bottom of the page, if you see if admissible, you know this means that the house is admissible. If you see this condition, it will be longer. It will take longer to realize this is a condition for the house being admissible. So we update maximum PPSF, and we also maintain the lowest PPSF among all admissible houses. So just to recap the Boolean type, so this is another primitive type in addition to int, float, double. It only has 2 values, true and false, and we can use and, or, and the not negation, the not operator, and it's typically used when conditional expressions are used, such as if statement and also the conditional part in the loop. So, so the next we're going to examine the provided code that are in HackerRank, but we'll do that in the next video.